Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Dear student, Assalamu alaikum. My name is Dr. Muslim Khan, Assistant Professor, Department of Chemistry, KUST. So today the topic of our discussion is nuclear magnetic resonance spectroscopy. And this topic is from a course whose code is CHEM451 molecular spectroscopy. First of all, NMR is the most powerful tool available for organic structure determination. It is used to study a wide variety of nuclei like hydrogen nuclei, carbon nuclei, nitrogen nuclei, fluorine nuclei, phosphorus nuclei. So we have already introduced in our physical lecture the nuclear magnetic resonance spectroscopy, but going to the background of the nuclear magnetic resonance spectroscopy, is you know that a nucleus with an odd atomic number or an odd mass number has a nuclear spin, and this nuclear spin, we are actually exercising this nuclear spin to get some information about the molecule. This spanning nuclei, this spanning charged nuclei, nucleus, generates a magnetic field like this. So this is a spanning proton, a loop of current basically, and it is acting like a bar magnet, which is having north and south pole. So when this is acting like a bar magnet, when this nuclei is placed, an external magnetic field, this spanning proton act like a bar magnet having north and south pole. So when this nuclei is placed, the spanning nuclei, so this will either align like this, align with external field or against the field. When this is aligned with external field, this is having a state which is known as alpha state, having low energy state or stabilized state. When this is aligned against the external field, this is known as a beta state or higher energy state. So a photon with the right amount of energy, this is a right amount of energy, can be absorbed and cause the spanning proton to flip. So this energy difference is basically proportional to the magnetic field strength, and the magnetic field strength is given as delta E is equal to h mu, and where this is equal to this. So this is the equation by which we know the relationship between energy and magnetic field. One of the most important terms used in the nuclear magnetic resonance spectroscopy is the shielding of proton. If all proton absorbed the same amount of energy in a given magnetic field, not much information could be obtained. Means that different protons in a molecule should absorb different amount of energy. But as we know that protons are surrounded by electron in the molecule that either shield them or deshield them, means either protect them or not protect them or less protect them from external magnetic field. So the circulating electron create an induced magnetic field that opposes the external magnetic field. So these shielded protons' magnetic field strength must be increased for a shielded proton to flip at the same frequency. So magnetic field strength must be increased for a shielded proton to flip at the same frequency. For example, this is a molecule, methanol molecule. Methanol is CH3OH. So it means that these are the protons which are more shielded because the energy difference between the electronegativity difference between carbon and hydrogen is not much. So means these electrons are basically almost equally share between carbon and hydrogen. So when these electrons are circulating, these are basically opposing the external magnetic field. It means that shielding these protons from external magnetic field. While on the other hand, because it depends on their chemical environment, proton and a molecule are shielded by different. On the other hand, this proton is bonded to oxygen atom. Oxygen is second most electronegative element in the periodic table. So these shared pair of electron between oxygen and hydrogen is more toward oxygen. So it means that when these electrons are inducing a field which opposing the external magnetic field will shield oxygen atom, not proton. So it means that this proton is less shielded, is deshielded by the action of oxygen atom. So this will absorb at a lower field, means at a lower field, and this will absorb at a higher field because you will see the you will see the spectra, that in spectra there is a higher field which and lower field is called down field, and higher field having higher energy is known as the up field. You will see it. So this is the difference. There is the difference between these protons. So in a spectra, you will see a peak for these proton in a different place and this proton in a different place. So NMR signal, the number of signals shows how many different kinds of protons are present. Basically, the number of signals in NMR spectra showing the different protons having different environment and molecules are basically shown. So the location of the signal shows how shielded or deshielded the proton is in NMR spectra. The intensity of the signal shows the number of proton of that type. For example, the intensity of 3 proton is more than the intensity of 2 proton and is more than the intensity of 1 proton. Signal splitting shows the number of proton on adjacent atoms. So I will tell you what is splitting in a spectra. So by the spectra, the information which is given is basically given from NMR spectrometer. What is what is NMR spectrometer? The instrument which is used to give us these information for a different nuclei, which what we have discussed is known as NMR spectrometer. What is there in NMR spectrometer? First of all, this is the sample tube, and this is surrounded by external magnetic field magnet, and here is a magnet controller, and there is a RF transmitter as well. So basically, in NMR spectrometer, we are measuring that how much energy, how much these radiation, radio frequency radiation, is absorbed by these nuclei. So this spectra is basically giving us that information, which is showing us the amount of energy absorbed by the sample, by the analyte. So this picture is adopted. This picture is adopted from this from Google, and the address is given. So NMR spectra is look like this for methanol, for a very simple molecule. So this basically spectra is starting from here. So this we will discuss it in our next slide, that for what this peak is. So basically, as I told you, that this side, which is near to this standard, what we have added to the sample, we add one standard. We will discuss it in next slide. And this part, which is more closer to the most shielded proton of standard, which what we have added to the sample. This is known as a up field or a high field. And when we are going away from this standard, this is known as a down field or lower field. So as we discussed in our previous example, that these 3 protons are more shielded proton, means very less energy is required to flip these proton. So it means that the signals for these proton must be closer to this standard. So this is signal for these 3 proton, and here it is more downfield, this because this is the de-shielded proton because of this electronegative element attached to it. So this is a signal for single proton, and the intensity of signal, this is signal for 3 protons basically. What is this standard that what we add? This is this is a signal for tetramethylsilane. Tetramethylsilane, there are basically 4 methyl group attached to the silane, and TMS is, this is known as tetramethylsilane. TMS is added to the sample, having these 12 protons, but these are the most shielded proton. These are the most shielded proton. It means that these are considered to be, since silicon is a very less electronegative element than carbon, is a less electronegative element than carbon. TMS proton are, means a very slight difference. these protons are highly shielded. So arbitrarily, the signals defined as zero for these tetramethylsilanes. So are all our other organic protons absorb downfield to the left of the TMS signals. And then when the shielding is increasing, when the shielding is decreasing, it is more going towards the downfield of the spectra. So this TMS, tetramethylsilane, is a, is a standard, considered to be a standard for NMR spectrometer. So uh, this when proton absorb energy and its spectra is more shifted from this tetramethylsilane, this is known as a chemical shift because it shifts from zero to the higher. Uh, so, uh, so this is measured in ppm, in parts per million. So this is the ratio of shift downfield from TMS in hertz to the total spectrometer frequency. For example, same value for 60,000 or 300,000 megahertz machine. So called the delta scale. You will see the delta scale. This is a delta scale. Chemical shift in ppm, shift downfield from MMS for any molecule in hertz and spectrometer frequency in megahertz. Like this is 60 megahertz for TMS 0, for TMS 0. So this is 220, 240 hertz. Like for this is for this machine. So this is basically the ratio of the shift of downfield from TMS divided by spectrophotometer frequency in megahertz. For example, location of the signal, more electronegative atoms deshield more and give larger shift value. For example, this is a very perfect example. Effect decreases with distance. Additional electronegative atom cause increase in a chemical shift. For example, ये हो this methyl chloride. Methyl chloride from 0 tetramethylsilane is shifted to 3 ppm. Only one electronegative atom is attached. This is dichloromethane. So when two electronegative atom is attached, it is more deshielding. So it will be more downfield, like to 5.30 ppm. So it means that same hydrogen proton attached at the same carbon atom, but the environment is changing. First, there were two other hydrogen atom and one electronegative atom. And now there are only one other hydrogen atom and two electronegative. So it is more shifted towards downfield. So the similarly trichloromethane. So then it is more shifted towards the downfield, like 7.27 ppm for this proton. Once, so for there will be intensity for 3 proton here, and it will be on a 3 ppm of a spectra, but it will be, the intensity will be less because the proton will be 2, and but it will be more shifted towards a downfield because of the attachment of another electronegative atom. And here it will be more shifted towards a downfield because 3 electronegative atoms will be attached. So these are the typical values for different protons. Like al- protons in alkane is having approximately a value of zero point 0.9 ppm, and protons in alkane, while it is attached to a CH2 group because environment is changed. This is when carbon is having three hydrogen attached. So in the neighbor, this hydrogen is having two, but in the neighbor this is having only one. So it is shifted 1.3, and alkane for CH 1.4. So similarly, CH3 C double bond O is for so it is more for acetone, it will be more towards 2.1. So one electronegative atom is attached. So for this hydrogen, acetylene 2.5, and similarly for this proton 3 to 4 when halogen is attached. When double bond, it is 5 to 6. Similarly, with the phenyl group 7.2, and this one 2.3, and aldehydic 9 to 10, and the carboxylic hydrogen 10 to proton 10 to 12. So for alcoholic variable bond 2 to 5, and like this. So these are the typical values. So from there you can say, so you know about the functional group of the molecule, that which type of hydrogen is present. So if the chemical shift is around 5 to 6 ppm, you say that there is a double bond and there in this molecule. If it is in the 9 to 10 regions, you say that I think this is hydrogen is of aldehydic group. So you easily know about uh, the the functional group of the atom, of the molecule. Uh, so G.D. Christian and Douglas Scugen and Crouch principle of instrumental analysis, also Wales Sperling atomic absorption spectroscopy. Uh, these are the books you can study for this. Thank you very much.